Hi, everybody. Welcome to the next set of talks. So next, we're going to have Kuikui, who is going to talk about spectral independence. So take it away.
Hi, everyone. Can everyone hear me okay?
Yeah.
Great, cool. So I'll be talking about spectral independence, which I guess you can think of it as like a different, like a more probabilistic or purely statistical formulation of some of the ideas we saw earlier this week on particular high dimensional expanders. Right, so I guess I personally come from this area. I work in this area called counting and sampling, and really just to give a little motivation, the main problem that we're interested in is the following. We have a distribution, given some distribution, U, and typically it's just for convenience, say on the Boolean cube. But we can think of say any product space or whatever we want, and our goal is to draw samples from U. So this is an exponentially large domain, but I want to do it efficiently, like a polynomial type. Okay. And some typical examples that we'll be interested in this talk are say classically studied combinatorial models. So for instance, a uniform distribution over stuff like matchings, independent sets, colorings, trees, and so on. And in particular, I'll be interested in settings where at least even the underlying support of the distribution has no apparent like algebraic structure or symmetries to it. Okay. And let me state just one more class of examples that is often studied in like say statistical physics settings or machine learning settings. And this is really like a weighted distribution. So here's one more example. So I have a matrix A. And I'm going to weight each configuration. So throughout, I'll write sigma for the plus minus one vector and dimensional. We weight each configuration as proportional to exponential, but quadratic form. So this is a classic example of an Ising model. It's a very non-uniform distribution. You should think of this matrix A here as being like the adjacency matrix, like a weighted adjacency matrix of some graph. If like say the entry, Aij is maybe one motivation for this will be something like you're like modeling a social network or something. If the entry Aijth entry is positive, then maybe person I and person J are like friends. If it's negative, then maybe they're enemies. And the plus minus one is just like a how they vote, for instance. Okay, these are just some like concrete examples to keep in mind. And again, let me emphasize, there's like there's not going to be like any like algebraic structure or symmetries to this. So the classical approach that's used in practice and theory that you probably know about is to run Markov chains. And let me just, for the rest of this talk, just focus on a very simple class and very classically studied Markov chain called Glauber dynamics. It's just given by the following two-step process. So say I'm starting at some configuration sigma. Okay. So in each step, I'm going to first pick a random coordinate I, say uniformly at random. Then I'm going to resample only the ith coordinate, condition on everybody else. Okay. Maybe to be a little bit more concrete, just in the case of the Boolean cube. So for instance, I will toss a biased coin where I flip the ith coordinate with this probability. Here, this x or I is just I'm flipping the ith coordinate. So with this probability, flip. How do I stay? Okay. So a couple notes. So for instance, typically I do not even know the normalizing constant to this distribution, but I can actually run this dynamics because I can compute the ratio because the normalizing constants cancel out. So this algorithm is actually implementable. Okay. I'm just going to keep running this two-step process over and over again. And second thing is that we need to know is that, and this is not hard to check, is that if I run this dynamics to infinity, then the distribution of the end state of my Markov chain is going to be exactly the distribution I want. Okay, so more formally, so you can, under very like mild assumptions, like say on connectivity of the distribution, you can prove that, so under mild assumptions, prove that for every starting state sigma, if I start from that state and I evolve the Markov chain for t steps, and I compare it with the distribution I care about, it's like polar variation distance, it's going to go to 0 as t goes to infinity. Okay. But of course, for algorithmic purposes, we really want this convergence to be fast. Like in polynomial number of steps, it's going to get to like say epsilon. It's going to get epsilon close to stationarity. Okay. What we really want now, fast mixing. If say for t less than polynomial, and say like log 1 over epsilon, TV, so get most epsilon. That's kind of what we want. Okay. So how do we typically approach this? Well, this is like this very beautiful observation that from many years ago that this mixing time is controlled by functional inequalities, okay, such as spectral gaps, such as log-Sobolev inequality. So let me just state those now. And these are intimately related to many of the functional inequalities that we've seen earlier this week. Okay. Let me define, I just want to state them, because our goal will be to develop new tools to establish these functional inequalities in these types of settings. Okay. So to define them, I need to first define quadratic form, something called a Dirichlet form. So, sorry, I guess I should have said P here is just the transition probability matrix of the Markov chain. Okay. So I'm going to find this quadratic form, E sub P. It'll consume two functions on the entire domain. And it's just given by the following quadratic form. So I look at the matrix I minus P. If you think of this as like a Laplacian, I'm going to hit it with the function G, take an inner product with F. And the inner product is a weighted one with respect to the stationary distribution. Okay. So if you want to see it, so just to give you an example, so for Glauber dynamics, for concreteness, this looks like I sum over all configuration sigma, mu of sigma. And now I look at the transitions from sigma. Times, basically the local variation of these functions across that transition. sorry, is this okay? Is this legible? Hopefully. And I guess, especially to some of you who would come from sort of analysis of Boolean functions, this kind of quantity should look very familiar. Okay, so I guess here I included, I guess, a very short dictionary, sort of translating between some of the concepts that are typically used in Markov chains and typically used in analysis of Boolean functions. So here you can think of the Dirichlet form as if I take G to be equal to F, and I look at, say, mu being the uniform measure of the Boolean cube, then this quantity is exactly the average influence of that function that we saw earlier this week. Okay. And there's a translation between the noise operator and the Glauber dynamics. And I guess I'll say in a bit what exactly is log Sobolev, but it'll be equivalent in a very precise sense to hypercontractility. Okay. Okay, so we have the Dirichlet form. And now I just need to tell you what are these functional inequalities that I'm going to use to control mixing. Okay. So these are the functional inequalities we want. So typically we start with sort of the E0 one, which is it's called a Poincare inequality, or the spectral gap. This just says that for all functions f, I have the following inequality. The variance respect to stationary distribution mu, the global variance is upper bounded by the local variance up to a factor of lambda. And it's well known that this implies, if you have such an inequality, this implies mixing in time order 1 over lambda times log of 1 over the minimum stationary probability. It's plus log. Typically, in say the Boolean cube, you'll expect the spectral gap to be like 1 over n. The minimum stationary probability will typically be exponentially small in n. So this would be like an n squared upper bound on the mixing time. But oftentimes we can get much better. So we can also ask for, say, entropy inequalities, which give a much sharper control on the mixing time. So a modified Log-Sobolev inequality, which is in some sense more appropriate for discrete settings, but it depends on the application, of course. So for all non-negative, okay, let's just say for all functions f, I have the following inequality: the global entropy of f squared, let's say non-negative. Global entropy of f is upper bounded by the Dirichlet form. Now I put f and I put log f here. Or if I change this to standard Log-Sobolev inequality, then I really have a very similar looking quantity. Now I've replaced the input functions to the Dirichlet form by something slightly strange. It's the square root of the function f. But the point is that if you have this stronger control in these two, this time stronger inequalities, then this implies, it's going to be legible from, okay, this would imply much better mixing. So in particular, we're mixing in time order 1 over either of these constants, except now I have log, and then log. Okay, so if I can get, like, say, a 1 over n lower bound on these constants, then I'll get n log n mixing, which is typically optimal. Say again? Sorry, okay, yeah, maybe I should define entropy. So So variance. Variance, make sure everyone's on the same page. Then entropy is similar. Now I place square by x log s. So okay, so our goal is to establish such functional inequalities.
For any intuition behind these inequalities?
So essentially, these come from these. What these allow you to do is control. So it depends on like how you measure convergence, right? So we typically measure in terms of total variation, but total variation is upper bounded by, say, relative entropy. If you want to measure things in relative entropy, and these two quantities exactly control the rate of convergence. Well, other questions?
I guess it's true for the modified log sublet.
Yeah, I mean, I guess you'd say that this is like a standard is like stronger than modified. There's a slight discrepancy in the discrete setting, but okay. So this is just, I guess, okay, so this is connection between mixing and sort of functional inequalities. Okay, so now I want to say what is this thing called spectral independence, which is how we're going to try to prove such inequalities. So remember, we're really working in a setting where there's no independence between coordinates, so classical strategies like tensorization are just going to fail. But we're going to sort of approach it by, in some sense, quantifying like how far your distribution is from truly independent. Okay. And I guess this should be also kind of remind you of like what Max talked about yesterday on like approximate product spaces, but it'll be slightly different in the definition. Okay, so now I want to define spectral independence. I wrote the same thing twice. Okay, let me explain that space. Okay, so in order to define what is spectral independence, let me define something called, so I typically call it an influence matrix, but since influence is such an overloaded term, I'm going to call it conditional influence. Okay, just to distinguish it from when you said analysis of Boolean functions. So I have a big distribution, but I'm going to define a very small matrix. Okay. So for all coordinates I and j, I'm going to find the conditional influence. Just this psi, it's just the difference of two marginal probabilities where I've conditioned on the presence or absence of the index. So normally if I sample a random configuration sigma, what is the probability that sigma maps j to +1, condition on knowing that I is mapped to +1, now minus the same thing. I've conditioned on I to be mapped to -1. So you can kind of think of this as also like an influence, or a conditional influence, because you're asking for how much does knowing the value for I influence the marginal probability for j.
Assuming that the marginals are biased.
Oh, no, I'm not going to assume anything like unbiased, right? So I have some arbitrary distribution. I can define correlations in this way. So now, okay, so I have this matrix. I can ask about eigenvalues and stuff. So I'm going to say, let's say mu is eta spectrally independent. If the largest eigenvalue. This is now, I can do this for I and j. This gives me an n by n matrix. So it's a small matrix. The largest eigenvalue is upper bounded by 1 plus A. It's the 1 is just for technical reasons. It's just coming from the fact that I equals j, and this difference is 1. Okay, so a few comments. First, this matrix is in general asymmetric, and it can have negative and positive entries. So it's not even clear that it has real eigenvalues. So what does this even mean? So the way to see that it always has real eigenvalues is by relating it to the covariance matrix of the distribution, which is something perhaps more familiar. So an equivalent way, equivalent formulation is to say that if I look at the covariance matrix, so I have plus minus 1 vector, so I can talk about the covariance. This is upper bounded in the PSD order by 1 plus eta times an appropriate diagonal matrix, where I put the variance of each coordinate. Okay. So using this, you can also then show that the influence matrix has real eigenvalues. So these are like two ways to think about what spectral independence means. It's just controlling all of the pairwise correlations in the distribution. Okay, let's see some examples. So in a moment, I'll tell you how this is related to, for instance, the notions of high dimensional expansion that we saw earlier this week. But I just want to first do some examples and state some what you can get out of this definition. See some examples. Okay, so does anyone want to tell me what the spectral independence of a product measure is? Other than diagonal, but the 1 accounts for the diagonal, so it's different. So other independence. That also kind of explains the name. So let's do the other extreme. I already gave it away. So now suppose I look at Pauling mixture. I take 1/2 probability, everybody all ones. 1/2 probability, everybody all -1. Okay, so what's the spectral independence of this? Exactly, right? All ones matrix, so the max eigenvalue is n. And -1 spectral. So, right? Because if I know the value of one coordinate, that determines everybody else. Okay. So in this case, the influence matrix is all ones. This implies n-1 spectral. You already see that there's two extremes, right? So this is a distribution with disconnected support. I expect Glauber dynamics is definitely not going to mix, and you can kind of detect that through how large the spectrum independence is. Let's see one last example, which is okay. So let's see one more example. So let's let U be uniform over, say, spanning trees. That's it, of course. So a classical result called the matrix tree theorem, which you might have heard of in the context of spectral graph theory and such, is that this distribution is negatively correlated. Okay? Because you can write this distribution using determinants, roughly speaking. So negative correlation. This means that so for all pairs of edges in my graph, if I sample a random spanning tree from the distribution, the probability that F is in the tree, condition on knowing is in the tree, is at most be not in the tree. So having another edge in the tree is only going to decrease my chances. Okay, so what does this say about the influence matrix for the uniform distribution over spanning trees? Yeah, exactly. So all the off-diagonal entries are non-positive. Right? Okay, so what does that say about spectral independence? So first, if I'm looking at the max eigenvalue, I can always upper bound it by, say, the infinity norm matrix. This is just, I look at the worst case choice of edge E and total influence of that edge on everybody else. Say conditional influence, okay? But now I can use the fact that all the off-diagonal entries are non-positive, so they're all the same sign. So I'm just summing up a bunch of probabilities, and I can use linearity of expectation. So this is really equal to the maximum of the choice of edge E. Of now, it's really just, instead of sum of absolute values, it's just the absolute value of the sum. I'll use, sometimes just for shorthand, I'll use E bar to note that the E is not in my sample tree. Okay, so this is exactly just, if I sample a random spanning tree, condition on having the edge E, what is the expected size of that tree? Well, clearly, if I know the edge E, I've contracted that edge, and I have a graph with n-1 many vertices. All spanning trees of such graph have n-2 edges, right? And similarly for this one. So this is just -2, -1, -1. So I can deduce a constant upper bound, a very nice constant upper bound on the spectral independence of the distribution using very classical tools.
And just subtract the diagonal, and then all the entries are non-positive.
Right. Yeah. But I guess you have a little bump. I mean, you can do better than this using something called log-concavity, but I'll get that later. Okay. But this is just using some very classical things. Negative correlation is like a very heavily studied topic.
Wait, how do you control these constants, spectral gap and constant?
Yeah, so I'll get there. So I just wanted to first say some examples, and now I'll now say like how, if you have spectral independence, what implications it has for these mixings. I just want this first. So any questions about like the definition? I mean, if you take nothing away, that's this. This one? So this always holds, right? So the eigenvalues are always upper bounded by matrix norms induced by vector norms. That's always true. Sorry. So I guess it is just this one. So yeah, so maybe. Infinity norm matrix is just I summation over J. So it's the matrix norm induced by the infinity norm, the vector infinity norm.
You're pushing the sum in the
Right, because I'm using the fact that all of these off-diagonal entries are the same sign. They're all non-positive. Yeah, I'm crucially using the fact that I know negative correlation for this distribution. It's not, I can't do this in general. Questions? let me state some theorems. Sorry, is there a question? Sorry, so the first theorem, and this is really just like a translation of some of these results in the area of high dimensional expanders. So this is really due to now. It says the following. So if the first, of course, I cannot deduce anything useful if I only impose this on the distribution itself. I need like a multi-scale condition, right? I cannot control it just based off the pairwise correlations alone. So if mu and all conditionals, when I say conditional, I just mean I pick a subset of coordinates and I put plus minus ones there, and then I induce a conditional measure on everybody else. Yeah, so for all exponentially many of these conditional measures, so if all of them are eta spectrally independent, then I can say gap, spectral gap of the Glauber dynamics is lower bounded by n to the 1 plus a. The eta goes into the exponent of the bound, but if eta is constant, which is what we're shooting for, that's like the gold standard in some sense, then this is polynomial mixing. This is only spectral gap, so this is nothing about log sub log or anything like that. But actually, okay, so we want more, of course, right? So for most like practical applications, of course, like n⁵ mixing is also kind of not acceptable. So we want to do more. So, but we need to add some assumptions. So at least for a lot of the applications that like say statistical physicists are interested in, like or these like, okay, I guess I erased it, but these like graph problems, like independent sets or colorings, they have an additional structure to them. And that's what we're going to add as an additional assumption. This is the second theorem. Suppose I impose the same condition. That's the first condition. Second condition is just that the distribution admits like an additional nice factorization property in the following sense. Mu satisfies what is something called, like, say, the global Markov property. Let's say something that's also called conditional independence. With respect to bounded degree graph. So I'll explain what exactly this means. So actually, yeah, I'll explain it now. So what does this mean? So imagine I have a distribution over plus minus 1 assignments to vertices of a graph. Okay. And I just wanted to satisfy the following property. If I condition on the values of the assignments to vertices in a separator, then in the resulting conditional distribution, the distribution of the configuration here and the distribution of the configuration here are completely independent of each other after I've conditioned on this, right? So this is kind of like if I have a graph and then, or I have like say two disjoint graphs who are not connected to each other, then the distribution of independent sets is just the product of the distribution of independent sets for each piece. That's this like nice sort of factorization property. And the bounded degreeness is just, sorry, not bounded graph, bounded degree. The bounded degree graph assumption is just so that I have some sparsity. So it's like, it's another way to quantify the correlations that are too strong. And the third is something which also has come up previously, is just that marginals. Marginals I just mean like the probability that a given coordinate is assigned plus or minus 1, those are all like constants. They're not like going to 0. So this is some technical assumption that perhaps if you remember from like say the analysis of p bias cube, this is necessary for getting something like a log subleft constant. This implies that, you know, say, hope it's okay if I just say lambda, rho, kappa are all lower bounded. So these are all these constants here. So, and 1 over n is the best thing you hope for, and this gives you n log n mixing for Glauber dynamics. Question? So typically I'll assume the graph is bounded to green, and in that sense, so I'll have this, and this will also typically be equal. Yeah, okay. So, and I guess there's a lot of other interesting works, say by Nima and also by Ronan Aldan and Yuan-Si Chun, which sort of, if you impose different set of assumptions, you know, maybe not that it comes from a graph, or you can even relax this marginal boundedness assumption, you can still deduce maybe not necessarily standard log Sobolev, but modified log Sobolevs. And those are all very interesting works, but unfortunately I won't have time to talk about this.
The whole thing become easy if you assume independence. Always independent distribution.
Not really, because I need this thing for all conditionals.
Can you repeat the question?
The question was just that does it become easier if I assume pairwise independence for the distribution? But you know, I need this for all conditionals as well. So if I assume pairwise independence, maybe I can improve like a constant here. But I want it for like many different like sort of levels, so to speak. If I understand the question correctly.
The process is that you have this almost pairwise independence after conditioning.
Right. So I want for all conditioning, I still have like a bound on these like.
Oh, okay, so that's exactly like the high-dimensional expander.
Yeah. So I'll say more precisely. So I guess okay, in like 10 minutes, I'll say like how like this is related to the notional high-dimensional expansion. It was really it came from there, like so that's how it came from. But like there is a reason why like we sort of stated this way. But okay.
Wait, also, like, how do you show that they have like the small parameters? Like, or something. So how do you show that? Like,
Which one? The marginals?
for instance, the first theorem. Like, how do I show that the eta is small for?
Yeah, that's not easy. So yeah, so that will be the subject of I guess the rest. So the end of this talk and also the next talk. So I'll show you some techniques that we developed to found this thing. Yeah, it's not easy.
Those influence matrices, they were like, I mean, the spectral independence definition is, I mean that's new, right? But like, didn't people study this matrix with like stronger bounds on it before?
Stronger bounds on it before.
But like bounds that are enough to give you like path coupling. This influence matrix.
Okay, if you're talking about, are you talking about like Dobrushin, for instance?
Yeah.
Yeah, so Dobrushin is, okay, I guess we can take this question offline, but roughly speaking, Dobrushin is, it's actually a slightly different matrix. So you somehow take an entry-wise maximum over all possible conditionings for each entry. In Dobrushin, I only have one matrix. Here I have exponentially many. And yeah, maybe it's a bit technical. We can take it offline. But okay, I'll say one more thing. If you have that condition, that Dobrushin, this will imply this condition. But this is weird. Exactly. More question. Okay, so I guess right. So I guess now I can erase some of this function inequality stuff, since really we're just going to focus on establishing this. Okay. I guess like my goal in this talk isn't necessarily to like prove like all the theorems or anything, but it's just to show you some examples and show you some techniques on how you verify this kind of condition. guess maybe I'll just give you so I guess I'll kind of outline like how the rest of the talks are going to go, and then I'll say the connection to high dimensional expanders and then show an example. Okay, so basically what we saw earlier is just that this notion of spectral independence so it implies fast mixing through those results. I also want to highlight there's a very nice other result in terms of getting concentration directly from spectral independence. So concentration. I mean, of course, you can always go from, say, a modified log Sobolev inequality to concentration, but there's a more direct way that sort of gets better, much better parameters, at least for linear functions. For linear functions. And even matrix valued is fine. And that's like really. This is due to Hoffman. Goes here somewhere. Okay. Anyways, yeah, I just want to highlight this. That's a very cool paper.
The L infinity definition or the L?
Yeah, so it's L infinity, the enclosed slightly stronger, but okay. Yeah, I just want to highlight this. I think it's a cool result. Okay, so this implies nice things. How do we verify this? So just as a high level overview, there are sort of several classes of techniques that we know how to use to verify this property. So first, let's say it's based off of various notions of coupling, and I'll actually try to, if I have time, I'll try to sketch one of these. Very cute example. The second is based off of something called geometry of polynomials. So you encode your distribution as a multivariate polynomial, and you study its analytic properties and use that to deduce probabilistic statements about your distribution mu. That's basically the subject of the second talk. There's techniques based off this thing called decay of correlations. This is like a classical structural property of the distribution that is often studied in statistical physics, but probably won't have time to get to that. And I guess the final one, of course, after I tell you the connection to high dimensional expanders, is the trickle down theorem. And then I guess, okay, so I told you, so I'm going to tell you maybe a bit about coupling today, geometry of polynomials in the next talk. And I guess tomorrow, I'll try to say some things about like proofs of these things. Okay, but for today, it's just how do you verify this condition? Yes. It's fine to, it's okay if I just erase this. So I just want to say very briefly the connection with high dimensional expanders. Okay, so what's the connection? So of course I need to build a simplicial complex out of my distribution. Okay, and this is something that was already helpfully done for me, essentially for me by Max and Irit. But I'm just going to just remind everyone what it is, what the construction is. So mu is on n. I construct a weighted simplicial complex. So let's call it x mu. Vertices correspond to pairs of coordinates, coordinate and assignment pair. I is a coordinate, S is an assignment. And then the facets, the maximal faces, they correspond to these sets of the following form, I, sigma I. So I guess pictorially, you can imagine like I have like all these coordinates. It's only 2 elements in here, but you just pick one from each and view that as a set. And of course, I'm going to weight it by the corresponding stationary measure. So I guess the reason I'm also doing this is because kind of a lot of the previous talks on high dimensional expanders, they did everything sort of in the case where the complex is like super regular, everything is uniform. And I thought it might be helpful to also state things when it's non-uniform. So everything sort of extends. So this is the simplicial complex. Okay, so now what is high dimensional expansion? So I'm going to use sort of the local spectral expander definition. So what is local spectral expansion? Really, what are the random walks? So I'm walking on a coordinate assignment pair, going to a pair of coordinate assignment pairs, and then coming back down. Okay. So the more general definition is of these local random walks in a non-uniform setting is the following. So I'm just going to call it QU. So it's going to, starting from a coordinate assignment pair, IS, it's going to walk to another coordinate assignment pair, JT. And to figure it out, it's going to be exactly equal to, after some normalization, the probability of a sample sigma mu, sigma j, t, sigma I. It's 1 over m in my slide. It's like the correct normalization. So of course, if your thing is super regular, then this is just uniform, right? It's just actually just a regular random walk. If your thing is non-uniform, then you weight things correctly by the marginals of the elements or the coordinate assignment pairs. And expansion is just saying that this local random walk has a spectral gap. So if I look at the second eigenvalue of this random walk, this is at most a Now, what's the connection between this and spectral independence? I guess first I'll say you can prove that the trickle down theorem also works in this setting.
Just a quick question.
Yeah.
So this is like the local walk at level 0.
Yeah, sorry. Yeah, this is at level 0. Then to get the ones at different links, then you just look at the conditionals of the distribution. Okay, so now let me state the sort of Oppenheim's trickle-down theorem and sort of the highest level of generality. Weighted simplicial complex. It says the following. So if Q mu is connected, and say for all coordinate assignment pairs, I have a spectral gap for local random walk after I've conditioned on coordinate I getting the assignment S, then I can say something about Q mu itself, where I no longer have this condition. And then let me just say, this is like an observation. Okay, so now this is really the connection between spectral independence and these local random walks. So we actually have an identity. So if I look at the second eigenvalue of this local random walk, this is equal to, there's no, this is an identity. This is equal to 1 over n minus 1 times max eigenvalue of the influence matrix. It kind of makes sense because the influence matrix has all these conditional marginal probabilities, and the 1 over n minus 1 just comes from the scaling here. Okay, so first this already says like, okay, you can use say trickle down to obtain spectral independence. And you might rightly wonder, okay, if I have this equivalence, why the heck would I define spectral independence to begin with? I guess I guess there are a few reasons. The original motivation for defining this notion was to capture the following phenomena. So if you notice in trickle down, the expansion degrades as you go down the complex, or as you sort of have fewer conditions. Okay? But in most sampling applications, what you actually observe is that it actually improves as you go down the complex. And that's where you see, like, if I have this as a constant, so this is saying bounded, but n is going to infinity, the expansion is actually improving as I go down the constant. So this spectral independence was sort of designed to capture that phenomenon. Okay, there's no degradation. I guess there are also like a couple, I guess maybe for me, like some nice aspects of spectral independence. So for instance, you can prove a very simple calculation that, for instance, if I look at the influence matrix of two measures and I take their product, that this has a nice block form. So in particular, analyzing product measures is very easy. I mean, easier. It makes things convenient for calculations. And I guess since I'm not so good at topology, I think for me it's easier to understand like influences, correlations, covariances, something a bit more familiar, more probabilistic. But of course, like, and I guess one more thing is also like once you have a lambda max, it becomes very natural to bound things using matrix norms. It's a very natural thing to do. Of course, everything's equivalent. You could do everything in this language. Okay, questions about the connection? Dor, do I have, how much more time do I have? 8 minutes? Okay. I'll try to sketch just one, I think a very cute example of how like you can use coupling to establish spectral independence. I guess if I don't finish this example, that's okay. I'll just continue the next one. Okay, so here's an example coupling spectral independence. So the example I'm going to work with is the following. So I have a graph G. Let's say its maximum degree is bounded maximum degree, just for convenience. And let mu is uniform over matchings. I mean all matchings, not just perfect matchings. I mean all matchings. So I include the empty set. Okay. Okay. So the claim, or what I want to prove, that mu is a delta plus 1, spectrally independent. And this in particular implies that Glauber dynamics okay. So first, a couple remarks, like historical remarks. So first, this model was studied, maybe not first studied, but the first, like I guess maybe major result on this was by Jeremy and Sinclair, which proved polynomial mixing or slightly different dynamics, not exactly Glauber dynamics, but for any, even the maximum degree can be unbounded, but just for simplicity, I'm going to work in the bound degree setting. And I guess this is also an illustration of like spectral independence in the sense that I don't know of like a coupling proof that this Markov chain mixes around. Okay. So how am I going to do this? I mean, coupling in like a classical sense. So yes, here's the lemma that we're going to use. So I guess first thing to note, it's like, if I condition on edge being in or out, then I just get the uniform distribution over matching instead of like a subgraph. Okay, so just without loss of generality, I can, and for convenience, I can just work with this really just the original graph G itself and the original distribution. Okay, so here's a lemma. So for all edges E in the graph, and also for all couplings, gamma of, say, distribution mu condition on E being in the matching, and mu where I condition on E being not in the matching, we have that's the total influence of this edge E upper bounded by the expectation where if I sample two matchings from the coupling and I look at the size of the symmetric difference, or if I think of them as like vectors, this is like Hamming distance between them. Basically, okay, if I have this, so I guess I'll also say this is due to. And the way we're going to prove this proposition is just to like construct this coupling iteratively. Okay. But let me first prove this. All we really need to do is just open up the definition of the influence. Okay. So if I look at, say, one particular influence, so I look at the probability that F is in the matching condition on E. Okay. So I like fix some F here. So this is exactly equal to if I look at, really you can think of it as I look at the total variation distance between, look at distribution mu, condition on E, and I look at the marginal on F. And I do the same thing where now I have condition on. So I'm really just comparing the flow variation distance between two conditional distributions. Flow variation distance admits by duality like a coupling formulation. I look at the best possible coupling such that I get the edge F to have the same status. Okay. So in particular, if I sum all of these edges F, is at most, if I pull the infimum over couplings out, of the expectation of, now I can use linear expectation, I sum over all edges F, this indicator. That's exactly this thing is exactly the symmetric difference between the two matchings. I just interpret influence as a total variation distance. Okay. I guess I can very quickly sketch then the coupling that you can construct iteratively for this application. I'll erase this one. Coupling. So I just imagine, I guess it's easier to use two different colors. So just imagine I have two copies of my graph. And in one of them, I'm assuming the matching contains edge E. And then the other one, I'm assuming it doesn't contain the edge E. And I want to sample a matching for the rest of the graph. And I want it so that these two matchings agree on everybody else as much as possible. Okay, so how can I do this? So this is the edge E. Now this edge E has some other edges coming out of it. I'm going to start sampling these edges one by one. Okay. So here's a question for you guys. Okay, let's just look at this vertex here. So look at vertex U. Vertex U. So in any coupling at all, how much can the disagreement between these two matchings propagate to this neighborhood? Does the question make sense? Okay, so remember, I want these two matchings to have the same, or very as close as possible, the same set of edges. Right? So I'm going to sample the edges, these neighboring edges, and I want to ensure that there's at most like minimize the number of disagreements. Let's just say for this neighborhood. Okay. So what is an upper bound on the maximum possible number of disagreements just for the neighboring edges? It's 1. Right? Because of the matching constraint, if any one of these guys, so first off, in this matching, all these guys have to be red, right? Because and so it's really just a question of which edge here is matched, right? If I pick one of them to be matching, that also kills everybody else. And so I can only have at most one disagreement. So the disagreement can only propagate at most once to a neighboring edge. Okay. So now I just need to. So I'm just starting from one edge, right? And I can propagate the disagreement to maybe at most like one other edge, then everybody else have to be out, right? By the matching constraint.
What about the other vertex?
So I can also do the other one, but I'm just going to start from one direction and then couple the rest of the graph. Let's build this coupling iteratively. The point is that the disagreement can only propagate at most once. So I just need a bound. So it's just everything's just controlled by the probability that this green edge happens versus it stays red, in which case all of these neighbors have coupled perfectly. And you can upper bound that probability by really the claim that you have to prove, which I won't have time for, because I guess maybe Dora will be mad at me. It's just claim is that the probability, let's say in this picture here, probably that this edge U has a matched edge condition on matching is at most maximum degree or maximum degree also. And this is not hard to prove, but maybe I have to get into that.
So we're a bit over time, but we have time for one or two quick questions. So any question for Kuikui? So let's thank Kuikui again. And we'll come back in 30 minutes.
Yeah, I know.